We're going to start chapter 17 today, which is a little bit more about acids and bases. We're going to look at something called buffers, and we're going to look at titration. And titration is a way of neutralizing acids and bases. Okay, so a buffer is a weak conjugate acid or base, depending on what you start with and what you end with. And what they do is they help resist drastic changes in pH. Give you an example. Okay, if you took two things of water, one was tap water, which has lots of buffers in it. Buffers would be the ions like calcium, magnesium, and so on. Or distilled water, which has no ions in it. If you put a drop of sulfuric acid in that distilled water, the pH is going to drop from like 7 to 2 with probably 1 or 2 drops. It'll drastically change it. To get it down to 2 in that regular, the tap water that has all the buffers, it would probably take 30 to 40 drops, okay? So basically what buffers do is they absorb either extra hydrogen or hydroxide, so you don't get these drastic changes in pH, okay? They contain relatively high concentrations of either the acid or base, okay? And when the concentrations are approximately equal, then you're going to get a neutral solution. And again, we're going to talk about more about that when we talk about titrations. But basically what a buffer does is it absorbs ions, whether they're hydrogen or hydroxide, so that you don't get this drastic change in pH, okay? One of the things you'll hear, I'm not sure which one of them, but it's some medication you can get right now, and they said they remove the citric acid buffer, which I don't really understand why they would do that, because it would make it easier. Another thing is if you look at your juices, lemonade, orange juice and stuff, they actually have buffers in them so that they're not so tough on your tummy, okay? Okay, so how do you make a buffer? Well, you can mix a weak acid and a salt of a conjugate base, or a weak base and the salt of its conjugate acid, okay? So in other words, you need to look at, remember, conjugate acids and bases, you need to use those in order to figure those out. You can add a strong acid and partially neutralize a weak base, or you could add a strong base and partially neutralize a weak acid, okay? So here's how it works. Here we've got, this is formic acid, or hydrogen fluoride, excuse me. Okay, if we add a buffered solution here, what will happen is, again, a small amount of acid or base will neutralize or slightly neutralize some component of the buffer. And what it basically, when you add it, absorbs those extra OH or H so that you don't get these drastic changes in pH. Okay, if you don't have a buffer in there, you'll get, huge changes. Like it might be a pH of around 2 and you add a little bit of a strong base and then all of a sudden it has a pH of 9. But if you add a buffer in there, it takes a lot longer. You can add a lot more. It absorbs things. And buffers, like I said, buffer and aspirin, if you remember that was one of the first ones, because when they first came out with aspirin, it was, it was good for getting rid of pain, but it wasn't so good on your tummy. So they started making buffer aspirin, bufferin, and it has buffers in it so that it helps absorb some of that, the nasty stuff, I guess, that comes out of aspirin, so it doesn't hurt your tummy so much. So really that's what buffers do. They make it so that things aren't so drastic. I don't know if that makes sense to you guys, but okay. So you can actually calculate the pH of a buffer. Okay, they have something called that's, I'll show you the formula, okay? This is how you rearrange it. You don't really have to know this part. This is all you need to know is right here, okay? If you want to find this new pH, you take the log of the K sub A. That chart that I gave you with K sub A and K sub B's, it actually has what they call the pKa. And really all it is the log of this number. And plus, what you do is you take the log of the conjugate acid over the acid, okay? So you take the log of this plus this, and you'll get your new pH, okay? This is how it all works out. So all of this is just mathematical rearranging, but this is what you're really looking for. So your new pH is going to be the pKa. You can do one of two things, okay? If you look up the Ka, you can take the log of that number and it'll give you the pKa, or if you go over one more column, it says pKa in it. It's your choice. You can do the log and then double check your answer if you want. And then this part, when I do these are the concentration, this is their molarity, okay? So you put these here, and so basically you're going to get the log of the, the log of these. You're going to take this number divided by this number and take the log of it. And then you're going to, if it's a negative number, you're going to subtract from this number. If it's a positive number, you're going to add it. And this is actually called the Henderson-Hasselbalch equation. It only works for buffers. Okay, you can't use it for anything else, but it only works for buffers. And again, these are the two guys that figure it out, how maybe to do all this stuff. But this is all we need to worry about, is this formula right here. Okay, so again, it's a way of figuring out what the new pH is. Okay, if you just add an acid to a base without buffers, it's going to drastically change it. If you add buffers, it goes much, much slower to a certain point. Then when all the buffer solution is used up, then it'll go fast. But again, it really slows things down for that. Okay, so here we have the pH of a buffer. It's 0.12 molars of lactic acid, which is, this is its crazy formula, and 0.1 mole of sodium lactate. So this is its salt with a part of the, because lactic acid would have hydrogen, this hydrogen here. Sodium lactate, you'd replace an H with an Na. Okay. The K sub A for lactic acid is 1.4 times 10 to the negative fourth. We have all the information we need. Okay. First thing we got to do is we got to find our pKa. All right. All you have to do again is take the log of this number. If you don't want to do that, just look on the chart that I gave you. Find lactic acid. It'll say this for the Ka, and then next to it has another column that says pKa. Put that number there. Okay. And then we have to take the log of the sodium lactate, which was 0.1, over the original acid. Okay. So it's always going to be the buffer over the original. Okay. So this number, the log of this is 3.85. And again, you can take this number and push log, excuse me, or you can just look in that column. It has it right there. If I take this number divided by this number and take the log of it, I get 0.018, a negative number. So now I'm going to subtract these. So now the pH of my buffer is 3.77. Okay. Originally the pH was what? 3.85. By adding the buffer, okay, then it just lowered it a little bit. Okay, so again, you take this number, take the log of the Ka, which is on that chart, but again, the pKa's are there also. So that's where I get the 3.85. It's the log of this number. I take 0.1 divided by 0.12, take that number and take the log of that number. That's where you get this. And then you just subtract them. That's all you have to do. Okay? Okay. The buffer's capacity is the amount of acid or base the buffer can actually neutralize before the pH begins to change a lot. Okay. If it's only changing like from 3.7 to 3.6, that's not a lot. That's only, a tenth. But if it starts going from 3.6 to 2.2 and then 1, that's a lot. So buffers have a capacity. They can absorb quite a bit. And then when they reach their max, when they've been saturated, they can't do it anymore. Okay. If you use the Henderson-Hasselbalch equation, the one I just showed you, pH will be the same for a conjugate acid-base pair of 1 molar each for every 0.1 molar you add. Okay, but the buffer, that is 1 molar. Okay, so if you have a buffer that's 0.1 molar each, it will work very well. But if the buffer is 1 molar, it will neutralize much more. So the stronger your buffer is, obviously, the more it can absorb before the pH changes. So if your buffer is just 0.1 molar, it's going to change a lot faster than if your buffer is 1 molar. That's a big change. Okay. All right, let's see. The pH range, it depends on the buffer system. Okay, the most common buffer system to use is citrate in foods. And again, if you want to look at some of your juices, look for sodium citrate. That's a buffer. Because you have citric acid in your juices, that's kind of tough on your tummy. So they also add sodium citrate to kind of, neutralize that a little bit. Okay. So when we're looking at the range, we want the optimal pH to be where the pH equals the Henderson-Hasselbalch equation. Okay. Or where these two are close to each other, where the acid with its the acid and its conjugate base are close to each other. We want their molarity to be similar, and then they'll work one. If one concentration is more than 10 times the other, the buffering action is going to be poor. So if you have a 1 molar versus a 0.1 molar, the 0.1 is not going to do very well. So if you have an acid that's 0.1, you want your buffer to be close to 0.1. Okay, then it works better. It'll last longer. Okay, this means that the pH range from a buffer is usually 1 pH unit from pKa. So you want it to be close. And again, you want their concentrations to be similar to each other if you want them to work. Okay, this is an addition of what happens when you add a strong acid or a strong base to a buffer. And again, it depends on their concentration. Okay, if you have a strong acid or base and you want a neutralization, you have to look at the stoichiometry. You have to look at, those 2s and 3s. And the second part of this chapter deals with titration, and I'll show you. That'll make much more sense. But when you're looking at buffers, okay, you want your buffer's concentration to be similar to the concentration of your acid or your base, whichever one you're using. Okay. Okay, and again, use the Henderson-Hasselbalch to find pH. Remember, it's pKa equals the log, and then you'll have your conjugate, or this is your acid, this is your conjugate base. Okay. Okay, here's an example. All right, we have a buffer, and what we did was we add 0.3 moles of, this is acetic acid. Okay, and 0.3 moles of sodium acetate. Okay, so this is its metal counterpart. Take off the H and add a metal, and that would be its buffer. And enough water to make 1 liter solution. Okay, calculate the pH after 0.02 moles of NaOH. So here's our acid. This is our acetic acid, and it's 0.3 moles in 1 liter. So if I'm doing my molarity, 0.3 divided by 1 is going to be 0.3. That's kind of nice. A lot of times they just give you the M. You're looking for the molarity. That's what goes here. That's their concentration. Okay. And then here it says we also have 0.3 of the sodium. Okay. So here's your acid. Here's its conjugate base. They're both the same. And our sodium hydroxide that we're adding is 0.02 moles. And again, divided 1 liter would be 0.02 moles. So it's the same. Okay. So what happens? Well, if we're adding this together, this is going to be 0. So this is our change. And these two are together, and these are our reactants. This is our product. So these two are going to be negative. This one's going to be positive. So now you add your numbers together. Now you've got your concentrations for your Henderson-Hasselbalch. Okay, basically that's what this chart does. So you're going to subtract whatever you added, your base that you added, and then do your calculations. That's where this comes from. That's where that comes from. Okay, and what I'm really looking for is these guys. So now, if I put my Henderson-Hasselbalch equation, okay, I look up my pKa for acetic acid, okay, which is 4.75. Again, that's on that chart. Now I'm going to take the log. Oh, sorry, I got to go back here. Here's my conjugate, and here's my acid. And again, your acid's always going to go on the bottom. Okay. So I put those in there. 0.32, 0.28. Okay, those come from my rice table. You love those rice tables. They came back again. Okay, and then now the pH, even though I'm going to add this base, because I have that buffer in there, instead of changing drastically, it's going to go from 4.75 to 4.81. That's not a huge difference. If you're using those little pH papers, it wouldn't show any difference. The only way you get these differences is with a pH probe. Okay, oh, and the next is titrate. Yeah. So, geez, we're almost at 15 minutes. So that was perfect timing. I usually don't do that. Sorry about that. Usually I run out. That's my thing. But again, when you're looking at a buffer, okay, it's basically take the pKa, which you'll find in the chart, and I'll put it in this one again, and then take the log of the two. This is your original. This is your buffer. Take the log, divide those two, and then take the log of it, and then add or subtract depending on which. In this case, it was add. It was a positive number. Okay, and that's it for this part of chapter 17.